Today we're going to talk about moles. Now, not the furry little garden pest that you might be familiar with, but instead, a mole in chemistry is a unit of measure. In fact, it's a very important number. So, why does this matter? Or how is it even used? Well, it turns out that moles allow us to count things by weighing them, which is a strange, idea, but this actually works. In fact, you've probably done it before if you've ever gone to a hardware store. So let's say, imagine that you want to build some amazing treehouse, somewhere that you can work on your chemistry homework in the peace and quiet that you deserve. Now, let's say you've estimated that you need 250 nails to finish this massive treehouse, and you find out that a dozen nails weighs 0.11 pounds. Okay, so not too bad. So the question is, how many pounds of nails should you buy? Because if you go to the hardware store and you tell the clerk, I need 250 nails, the clerk's not going to sit there and count them out for you. Instead, he or she will just say, well, how many pounds do you need? And that's it, right? So how do we actually go about doing this? Well, we can actually use the domino method that we learned earlier, dimensional analysis. So what I'm going to do is I'm going to go ahead and set up my problem with a number in the top left-hand corner. And what number should that be? Well, remember that we don't want to use this because this is a conversion factor. So we're not going to put that in the top left-hand corner. That's actually going to go somewhere in the center here. We're going to go ahead and put this number, 250 nails, because that's really the only number that's not a conversion factor that's given in the problem. Now, this seems weird that we're using units like nails, but that's perfectly acceptable. Now, what's my question mark? Well, the question asks, how many pounds of nails should you buy? So my question mark is actually pounds. Alright, now how do I go from nails into pounds? Well, I do see that I have this conversion factor here that will easily let me go from dozens into pounds, but I need to change these nails into dozens. But that's pretty easy, right? Because we know that 12 nails is equal to 1 dozen, right? And because we know that a dozen is just kind of a unit of measure or unit of counting, and it means 12, right? And it doesn't matter whether we're talking about jelly donuts or calculators or elephants or nails, it's always 12, right? Now, notice that my units here for nails cancels out top and bottom, but I'm still stuck with dozens. I need to change that. But luckily, I have that handy conversion factor that we mentioned earlier, and this says that 1 dozen nails actually weighs 0.11 pounds. So let's go ahead and double check that all of our units cancel. Dozen cancels dozen, that's perfect. Pounds cancels pounds, which is great because that means that everything cancels out. And so now all we need to do is multiply all of the top numbers together. So this comes out to 250 times 1 times 0.11, which is equal to 27.5. On the bottom we have 12 times 1, which is 12. So we're going to write 12 here on the bottom. And then we need to just go ahead and divide the top number by the bottom number. And this comes out to 2.292. Now we need to check our sig figs, right? Because we should always make sure that we have the correct number of sig figs. If we look at this, we have 2 sig figs in our original number here. Notice that that's a trailing 0 there at the end. There's no decimal point in the number, so therefore we only have 2 sig figs that we can keep. So we have the 2 and the 2, but it turns out that we should actually round this to 2.3. We should round that 2 up to a 3 due to the 9 next door to it. And what are my units? Well, my question mark was pounds, so that has to be my unit. So in this case, all we've done is we have determined that if I want to buy 250 nails, I need to purchase 2.3 pounds of nails, and if I were to count those out, I would find out that it came out to 250 nails. Alright, so I've actually I've counted nails by weighing them. Now let's change things up a little bit in our scenario. What if you decided that you want to buy larger nails? The ones that you just purchased aren't hacking it. So we need, instead of like tiny little nails, we need some big old massive nails. So here are some questions. Would a dozen nails still weigh 0.011 or sorry, 0.11 pounds? Well, no, because we've changed the size of the nails, and therefore we've changed the mass of the nails. So that would not be true. But would there still be 12 nails in a dozen? Well, yeah, because 12 is still a dozen, right, by definition. Now this is going to directly correlate to when we discuss atoms, right? If I talk about a dozen atoms, well, a dozen atoms is 12, right? But gold atoms weigh a lot more than helium atoms. And if we look at our periodic table that we've been discussing, we can see the atomic weight or the atomic mass of those various atoms, and we can see that definitely some atoms are much, much larger and heavier than others. So this is where we get into what's known as Avogadro's number. So Amadeo Avogadro was a very famous scientist, and he didn't actually come up with this number, but because he was so important and has such an awesome name, they went ahead and named this number after him. So Avogadro's number is sometimes abbreviated N sub A, right? So Avogadro's number. And this is kind of a definition, right? So just like we know that 1 dozen is always 12 things, right? What if I said a dozen? You'd say 12. If I said a baker's dozen, you would say 13, right? Well, a mole is kind of like saying a chemist's dozen. So 1 mole is defined as being equal to 6.022 times 10 to the 23rd things. Now, I could have a mole of oxygen atoms, which would be 6.022 times 10 to the 23rd oxygen atoms. I could have a mole of, I don't know, a mole of spiders. I could have a mole of desk lamps. It doesn't matter, right? It's a number. It's like saying a dozen. Now, this number is a huge number. I mean, 6.022 times 10 to the 23rd, so 10 to the 23rd. I mean, you're basically saying 6 with 23 zeros after it. I mean, that's a huge, huge number. In fact, it's really hard for our brains to kind of wrap themselves around how truly large this number is. So, let me give you an example. Let's say that you're walking down the beach one day, and you come across an old lamp buried in the sand. And as you pull out this lamp and you start to rub it to kind of clean it off, you suddenly see this genie pop out. And of course, like most genies, it's a chemistry genie, right? And so this genie says, I will grant all of your wishes in moles, right? So you have 3 wishes, but all of them will be granted in terms of moles. And you're like, well, this seems like a pretty sweet deal. And you're thinking to yourself, well, what should I ask for first? Well, the first thing I want is I actually want some marshmallows, right? Some tasty little marshmallows. I only want some, little mini marshmallows because I'm going to, I don't want to be greedy, and I'd like to, have a little s'mores roast here on the beach. So you wish for 1 mole of mini marshmallows, okay? And suddenly the genie snaps his fingers, and he grants you 1 mole of mini marshmallows. And 1 mole of marshmallows would actually cover the entire Earth to a depth of about 50 miles. So that's a lot of marshmallows. You'd be like swimming through it with your mouth open and like chomping on them. It'd be pretty nice. So after you have this wish granted, you suddenly decide, well, you know what else would be really, really nice? Maybe having some money, right? So you go ahead and you wish for some money, but you don't want to be greedy again, and so you wish for pennies, right? So you wish for 1 mole of pennies, and suddenly you have 1 mole of pennies stacked up, and it turns out that this is a lot of money. I mean, even if you spread your wealth amongst every man, woman, and child living on the entire planet Earth as of this moment, you divvied out this money equally, and we all spent $1 million a day till the day we die, you'd still have half the money left over once the current population has died out. That's a lot of money, right? And so, yeah. So you think, well, what else do I really, really want? You think, well, on YouTube I saw this cool video in which someone took some hydrogen and they mixed it with oxygen gas, and then they ignited it and it made a big bang. That sounds like a fun little demo. So you wish for 1 mole of hydrogen. Okay, and 1 mole of hydrogen molecules would weigh about 2 grams, which is about the mass of 2 paper clips. So not a whole lot, right? well, why is this such a small amount when all of these amounts over here were huge? Well, numerically they're the same, 6.022 times 10 to the 23rd. However, the difference is that atoms are extremely, extremely small, right? And so therefore, you can, 6.022 times 10 to the 23rd atoms or molecules doesn't seem like a whole lot when you actually, weigh that out. And again, some atoms will weigh more than others. Now, this seems kind of like a silly example, but remember that this is a really important number. In fact, we use it in chemistry every day. So let me give you a few more pointers that are actually pretty important. One is that you should know this number. You should definitely know that 1 mole is equal to 6.022 times 10 to the 23rd atoms. And we can use that as a conversion factor, right, as a domino. And we're going to see some problems like that in just a minute. But the other thing that you should note is that there is an abbreviation for mole. It's M-O-L. So I saved you an entire letter, so you can thank me later. But do not get confused with molecule and mole. They are two different things, right? A mole is 6.022 times 10 to the 23rd. Now, the other thing that you should be aware of is that this number is so important that there's an International Mole Day, which you can probably guess occurs on 10/23, October 23rd. So every October 23rd is International Mole Day, and this is a pretty big deal. I mean, Google it. It's like there's a theme song, and sometimes people do fireworks, and there's like a mascot. All kinds of good stuff happens. I usually have a big party in my class for International Mole Day, so this really is a big deal. Make sure you remember that date. Alright, so now that you remember International Mole Day, let's say that you decide to buy a ring for that special someone for Mole Day, and you go shopping at the jeweler, and they're having a special on Mole Day rings, and the salesman says, well, I can sell you this gold ring here, and it contains 4.77 times 10 to the 22nd atoms of gold. And you're like, oh wow, that's great. But you know that when you give it to that special someone, the first thing she's going to ask is, well, how many moles of gold does it actually have? So before you give it to her, you should definitely do a quick domino problem and calculate this thing. So how do we work this? Well, what number are we actually given in the problem? Well, the only number that's given is 4.77 times 10 to the 22nd, and this is in terms of atoms. Okay, gold atoms in particular, but atoms. And then down here, we want to know how many moles. So question mark, moles. We're going to go ahead and put that in the bottom right-hand corner. All right, now what domino are we going to use here in the middle? Well, anytime you see the word atoms or molecules in a problem like this, you know that you have to use Avogadro's number, which remember says that 1 mole of anything is equal to 6.022 times 10 to the 23rd atoms or molecules or bicycles. It doesn't matter, but what this thing is here. In this case, we're talking about atoms, so we're going to make sure that it says atoms on that part of it. Okay, so let's go ahead and put our 1 mole up on top, and we're going to put our 6.022 times 10 to the 23rd atoms down on the bottom. Now, why did we put that on the bottom? Well, because that way it cancels. Atoms top, atoms bottom, moles on the top, moles on the bottom. Everything cancels out. And so therefore, all we need to do is we just need to plug this into our calculator. So multiply across the top, 4.77 times 10 to the 22nd times 1. Okay, and then divide that by 6.022 times 10 to the 23rd. Now, personally, I always put scientific notation in parentheses whenever I'm entering this into my calculator, because otherwise it might mess things up. So I'm going to go ahead and enter that as 4.77 times 10 to the 22nd divided by parentheses 6.022 times 10 to the 23rd. All right, and this came out to be 0.0792. Okay, If you got a number that's different than that, you probably, if you got something that says like 10 to the 45th or something, you probably forgot your parentheses. Now, a couple things here. What are our units? Well, our units have to be moles, because that was our question mark. Next, let's go ahead and check our sig figs. Notice that our first number, 4.77, had 3 sig figs, so our final answer can have 3 sig figs. So it already has 3 right there, and we can go ahead and just circle that, because that's our final answer. So when you hand this to that special someone for mole day, you can say, hey baby, this contains 0.0792 moles of gold. And that's sure to impress. Okay, so now you've purchased a ring for that special someone. Now you go ahead and head to the party store and you order some balloons, right? Because, balloons are fun for mole day. And you get some balloons filled with helium. And you give it to your kids, and the first thing your kids say is, wow, this is great, Dad. But how many atoms of helium does it actually contain? Right? Kids are always asking questions like that. So, in this case, luckily, the person at the party store told you that it contains 0.87 moles of helium. And now you want to know how many helium atoms does it actually contain. Well, luckily, we can go ahead and set up another domino problem. So you can have your kids do this with you, because I'm sure they'd love it. Let's go ahead and put our 0.87 moles in the top left-hand corner. And let's go ahead and put question mark helium atoms in the bottom right. All right. Now, notice that again, we see the word atoms in this problem, which means that we're definitely going to need Avogadro's number. So, do I want my 1 mole on the top or the bottom? Well, this time I want it on the bottom so that it'll cancel. And then on the top it has to say 6.022 times 10 to the 23rd atoms, or in this case helium atoms to be precise. Alright, check myself before I wreck myself by messing up my units. So moles cancels moles, helium atoms cancel helium atoms, and I know I've set up this problem correctly. So now all I have to do is multiply 0.87 times 6.022 times 10 to the 23rd and divide by 1. So let's go ahead and enter that. 0.87 times 6.022 times 10 to the 23rd, and it comes out to 5.23914 times 10 to the 23rd. Now, your kids obviously care very deeply about sig figs, so you got to make sure your sig figs are correct. Our starting number had 2 sig figs in it, so we can only keep 2 sig figs at the end of the day. So I'm going to go ahead and round that to 5.2 times 10 to the 23rd. Notice that when I'm rounding my sig figs, I chop off here, but I need to keep this, the 10 to the 23rd. Those are placeholder zeros. They don't count towards my sig fig limit. Oh, and then what are my units? My units must be atoms, or in this case helium atoms. And so you can proudly tell your kids, that balloon contains 5.2 times 10 to the 23rd helium atoms. And then, for a really fun activity, you can you can do something like this. You can say, well, kids, let's imagine that you wanted to count all of those helium atoms, and you're really good at counting, right? So you can count, about 1 number per second, right? 1, 2, 3, 4. So let's figure out how long it would take you to count all of those helium atoms. Let's try that real quick. All right. So 5.2 times 10 to the 23rd atoms. And I want to know how many years it would take to count all of those. So I can count about 1 atom per second, right? If I'm just counting 1 atom per second. I know that 60 seconds is a minute. This has absolutely nothing to do with the class, but I just think it's kind of fun to try some dimensional analysis, because this is such a useful technique. Plus it's fun. You might not think so, but So 60 minutes is 1 hour, right? 1 hour. Oh, sorry, back that up. 24 hours is 1 day, and 365.25 for counting, leap days. Days is equal to 1 year, right? Double check that everything cancels. Atoms cancels atoms, seconds cancel seconds, minutes minutes, hours hours, days days, years years. All right, so everything cancels. Let's go ahead and plug this in. So 5.2 times 10 to the 23rd, and we're going to divide by, and I'm going to put all of these bad boys in parentheses way down at the bottom. So 60 times 60 times 24 times 365.25 divide, and it comes out to about 1.6 times 10 to the 16th years. So that would be a 1, 6, and then 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 years. So let's see, that's 1,000, that's 1,000,000, that's 1,000,000,000, that's 1,000,000,000,000. That would only take about, what is that? So that's 1,000, million, billion, trillion. It only takes 16,000 trillion years to actually count all of the helium atoms in that balloon. So you can see that these are huge numbers that we're dealing with, right? Not something that our brains are really equipped to deal with. But if you were to inhale that helium, then you could count all of those atoms, for the 1.6 times 10 to the 16th years with a very high Mickey Mouse voice. Now this seems really great, right? I mean, we can do all kinds of crazy calculations with this. We can go from atoms into moles, or moles into atoms, or molecules into moles, or moles into molecules, back and forth using this extremely handy number. But in the lab, you'll notice that all of the balances all have to do with grams, right? They can't weigh things out in moles. So there must be a way to go from grams into moles, and luckily there is, my friend. So if you were to pull out your periodic table, you would see, a little box like this for, let's say, magnesium, and let's go ahead and look at this number on the bottom. Now we've said that this is the atomic mass, or the atomic weight, right? But there's something really important about this. It turns out that this number tells us, oops, back up 1 second. Okay, this tells us that if you could somehow pick up 1 atom of magnesium and put it on a tiny, tiny scale, it would actually weigh 24.31 atomic mass units. Okay, that's the weight of 1 atom of magnesium. But the really cool thing is that if you could count out 1 mole of magnesium atoms, in other words, if you could count out 6.022 times 10 to the 23rd magnesium atoms, stack them all up on a scale, that scale would read 24.31 grams. So that's why this number is so amazing, because Avogadro's number acts as a conversion factor that seamlessly takes this number and tells us the mass of 1 atom, but also tells us the mass of 1 mole of atoms, which is also why there are no units on these masses, right? Because the mass is AMUs if we're talking about a single atom, or grams if we're talking about an entire mole of atoms. So let's go ahead and actually practice using this. So I want you to go ahead and help me to figure out the formula weight of these things. So what's the formula weight? Well, it's pretty simple. All we're going to do is we are going to go ahead and look at our periodic table for carbon dioxide, right? We're going to look at carbon and 2 oxygens and add up the masses of those. So carbon is 12.01, and since we're talking about just a single atom of this, it would be AMUs. And now we have oxygen, right, which is 16.00. I should mention that some periodic tables go out to like 5 or 6 decimal places, and that's great. You can use that. The periodic table I carry around only goes out to 2 decimal places, and so that's what I do. I usually just go out to 2 decimal places. So, please do not freak out if there's some kind of discrepancy, just a slight discrepancy when we are adding things up. It'll all come out in the wash, so don't worry about it. But notice that in our CO2 we have 1 carbon and we have 2 oxygens, right? So I actually need to do 2 times this, and then I can go ahead and add this thing up, right? So 12.01 plus 2 times 16 comes out to 44.01 atomic mass units. So if I could somehow pluck 1 molecule of carbon dioxide out of the air and place it on a scale, it would weigh 44.01 atomic mass units. Now let's try the same thing, but with magnesium carbonate. So magnesium weighs 24.31 atomic mass units, and carbon is 12.01 atomic mass units, and we just said the oxygen is 16 AMUs, but notice again that there are 3 of those, right? So 3 times that, and we just need to add this whole thing up. So we've got 24.31 plus 12.01 plus 3 times 16. So that's 84.32 AMUs, okay, or atomic mass units. So we just figured out the formula weight, right? The formula weight of these things, right? The weight of just 1 molecule by looking at the periodic table. Now, the next thing that we could do is we could go ahead and figure out the molar mass, right? Molar mass means if we could somehow count out 1 mole of molecules, what would the mass be? And so it turns out that this is really easy because all we have to do is just erase anywhere it says AMUs, and we're going to go ahead and put in grams here. So what this means is if I could weigh out 1 mole of carbon dioxide molecules, it would weigh 44.01 grams, right? This is great. Now, I personally like to write that this is equal to 1 mole of CO2, right? Because this is going to come in handy when we do conversions later on. So remember that anytime you add these up on the periodic table in grams, that's the molar mass. That's the mass of 1 mole. So let's do the same thing over here on our magnesium carbonate. So we can go ahead and erase out all the AMUs. And now, let's go ahead and put in grams. All right, so 84.32 grams is equal to 1 mole of MgCO3. All right. All right, just to make sure that we have this down, let's go ahead and try a few more examples. These ones will be just a little bit trickier, just to make sure that we have this, because this really is an important skill that we're going to be using throughout the entire course. So let's go ahead and look at this next example, which is ammonium sulfate. This one's a little bit trickier because notice that the ammonium ion is here in parentheses, and there's a 2 outside. That 2 means that we have 2 nitrogens and 8 hydrogens, right, because 4 times 2. So we need to take that into account when we are adding these things up. So nitrogen is 14.01 AMUs, and we happen to have 2 of those. We have 8 hydrogens at a mass of 1.01 AMU. And again, don't worry if your periodic table says 1.0079 AMUs. It won't matter once we add in, around to sig figs. So let's see, this comes out to 32.06 for sulfur. And we also have 4 oxygens at a mass of 16 AMUs each. If we add this whole thing up, let's see what we get. 2 times 14.01 plus 8 times 1.01 plus 32.06 plus 4 times 16. Looks like 132.16 AMUs. Okay, looking at sig figs, notice that this is an addition problem, and all of our numbers have 2 decimal places, so we can have 2 decimal places in our final answer. So let's go ahead and move on to this one. This is glucose over here, C6H12O6. So we have 6 carbons at a mass of 12.01 AMUs each. We have 12 hydrogens at a mass of 1.01 AMUs, and 6 oxygen at a mass of 16 AMUs. Add up this whole thing. 6 times 12.01 plus 12 times 1.01 plus 6 times 16. This comes out to 180.18 AMUs. So that would be the what's known as the formula weight of glucose here. Now, how do we get molar mass? Remember that this is easy, right? All we need to do to get molar mass is simply erase anything that says AMUs and switch it for grams. So 132.16 grams is equal to 1 mole of this stuff. And over here, we'll get rid of our AMUs. Enter grams in its place. And we now know that 1 mole of glucose would have a mass of 180.18 grams. Okay, let's try putting this into a word problem and see how this works. Alright, in this case we have 2.47 grams of lithium carbonate, and we want to know how many moles is that equivalent to. Well, let's go ahead and set up our domino problem. And I'm going to go ahead and put 2.47 grams in the top left-hand box, and let's put question mark moles down here in the bottom right. Okay, that'll allow us to go from grams to moles pretty easily. Now we're going to need a domino somewhere here in the middle, right? A domino that allows us to go from grams into moles. Luckily, anytime you go from grams to moles, you're going to use the molar mass, right? We mentioned anytime you go from atoms or molecules into moles, you're going to use Avogadro's number. Anytime you go from grams to moles or moles to grams, you are going to use the molar mass. Okay, so how do I get the molar mass of lithium carbonate? Well, I can go ahead and add those up on the periodic table. So I know that this is Li2CO3. So what I need to do is look up the mass of lithium, which is 6.94. So 2 times 6.94 grams plus 1 carbon, which is 12.01 grams, plus 3 oxygens. Each one of those is 16 grams a pop. Add that whole thing up, and let's see, 2 times 6.94 plus 12.01 plus 3 times 16. So this comes out to 73.89 grams. And because I added that up on the periodic table, I'm going to say that that's equal to 1 mole. Why do I bother writing that out? Well, because when I plug it in here in my domino, I'm going to write 73.89 grams on the bottom so that the grams will cancel, and I'm going to make sure I write 1 mole on the other half of this domino. Anytime you add things up on the periodic table, the other half of the domino has to say 1 mole. Okay? Grams cancel grams, moles cancels moles. Everything cancels, so I know I've set this up properly. And now it's 2.47 times 1 divided by 73.89. So 2.47 divided by 73.89. And this comes out to be 0.006 3, 3, 4. My units are moles. You know, if on an exam or something, if all the answers were in scientific notation, I'd simply write this as 3.34 times 10 to the, let's see, I moved the decimal 1, 2 places, and it's going to be negative because I moved it to the right, or in other words, this is a really small number, much smaller than 1. So therefore, my final answer is going to be 3.34 times 10 to the negative second moles, or 0.0334 moles. Either one's correct. Okay, let's go ahead and try one more. All right, then this last one we're going to chain everything together, okay? So let's try this one. 9.33 times 10 to the 27th molecules of CO2 is equivalent to how many grams? Well, this one's going to be a little more work. So let's go ahead and try this out. Okay, what goes in the top left-hand box? Well, there's only one number given, right? 9.33 times 10 to the 27th, and this is molecules. Oh, let's see, can't seem to write that. Let's try that again. Molecules. Need a little more space. I'm just going to write it down here. Apologize for that. All right, times 10. So 9.33 times 10 to the 27th molecules. What goes in the bottom right? Well, this is going to be question mark grams because it's asking how many grams, right? Now, in this problem, notice that it mentions the word molecules, which means I know that I'm going to need Avogadro's number, right? Which says that 1 mole is equal to, hopefully you remember this number by now, 6.022 times 10 to the 23rd molecules. All right, and then notice that this problem also mentions grams, right? And anytime you're going from grams to moles, you need molar mass. To get the molar mass, we're going to have to pull out our trusty periodic table and add things up. So let's go ahead and do that over here on the left-hand side. So carbon dioxide, CO2, we know that carbon weighs 12.01 grams. I'm getting these numbers straight off the periodic table. We have 2 oxygens, and each one of those weighs 16 grams. And just so you know, there's no reason to memorize all these numbers, but you will find that over time, you'll probably start to remember them just because you use some of them like oxygen and hydrogen and carbon so often. All right, add those up and it comes out to 44.01 grams, and that's equal to 1 mole. All right, so let's go ahead and we can insert that back up here in this domino, right? Where do I want my 1 mole? On the bottom, because that way it will cancel. That means that I have to write the 44.01 grams on the other half of this. Now let's go ahead and double check that everything cancels out. Molecules cancels molecules, moles cancels moles, grams cancels grams, which means that I know I've set up my problem correctly. Now it's just a matter of actually crunching the numbers, right? So again, whenever I'm using scientific notation, I like to put it in parentheses just to be safe, but I'm just going to multiply all the top numbers. So I'm typing in 9.33 times 10 to the 27th times 1 times 44.01, and I'm going to divide that entire thing by parentheses 6.022 times 10 to the 23rd. Okay, times 1, and let's see, this actually comes out to be a huge number. 6.81855. Well, that's pretty big, right? This is in grams because that's what my unit is up here. All right, so how many sig figs can I have? Well, looks like in our original number we only have 1, 2, 3 sig figs, so we can only have 1, 2, 3 sig figs. Okay, so, well, let's see, how are we going to round this? Well, we can round this to 6, 8, Now, do we round that up to a 2 or down to a 1? We're going to round it up to a 2. Now, do we leave it as just 682? No, this wouldn't make any sense. If this were my bank account, I wish, then I wouldn't say, oh, I have approximately $682 in there. I would say, I have approximately $682,000 in the bank. Okay, notice that these are not significant zeros because there's no decimal point in here, right? So I can go ahead and write it like this, 682,000 grams, and I can leave it like that, or I could go ahead and convert that into scientific notation just for fun, because nothing says fun like scientific notation, right? 6.82 times 10 to the, let's see, we'd move it 1, 2, 3, 4, 5. So 6.82 times 10 to the 5th grams. And that would be a perfectly acceptable way to write it as well. All right, so this is how we go from grams to moles, right? Or moles to grams. We use the molar mass. If we want to go from molecules or atoms into moles, or moles into atoms or molecules, we use Avogadro's number. If the problem mentions both molecules and grams, or atoms and grams, you're going to have to use both of those somewhere along the way. And we can kind of flip things around and move them however we need to. We just have to make sure that our units cancel. So let's go ahead and just have some fun now. Not that it isn't, wildly fun just to do a whole bunch of these molar mass problems, but I'm going to go ahead and show you how we can, count things like cards using something as simple as, a little magic. All right. So let's go ahead and we've got a deck of cards, and I'm just going to go ahead and cut the deck wherever. It doesn't really matter. And it turns out that just by weighing this, I can actually figure out that there are 22 cards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 cards. Okay, simply by just weighing what's left of the deck. Now it gets even better. I can cut the deck anywhere I want. Okay, and without even looking at it, I know that the card we cut to is the 10 of clubs. Now, obviously, it would be a bit more exciting if you were here. I'm actually doing it, but that's it for moles. All right, I hope you enjoyed it.